China's railway network has become the beating steel artery of a nation in motion. Behind this vast system lies one of the most advanced track-laying operations on Earth. Here, every rail, each weighing hundreds of kilograms, is placed with micron precision by fully automated machinery designed and built in China. Massive yellow giants crawl forward, lifting, aligning, and welding the rails into seamless ribbons of steel that stretch beyond the horizon. But have you ever wondered how China can lay tens of thousands of miles of steel rails with such speed, precision, and power? Let's find out with Mandarin Tech. In the United States, most railway lines are still built using the traditional method, with thick layers of crushed stone, known as ballast, laid beneath each rail. This seemingly simple material plays a crucial role. It distributes the train's weight, keeps the track structure stable, and allows rainwater to drain away from the track bed. China, on the other hand, has taken a completely different path. On its next-generation high-speed railways, the traditional layer of stone has been replaced by a continuous concrete foundation, known as slab track. Here, the rails are fixed directly onto the concrete surface, aligned with laser systems, and installed by fully automated machinery. Instead of loose stones, the entire structure becomes one unified body, stronger, more durable, and incredibly precise. As a result, Chinese trains can travel smoothly at speeds exceeding 350 kilometers per hour. And now we're going to the construction site to see how they complete thousands of miles of railway. The subgrade is prepared by grading and compacting multiple layers of soil and gravel until a firm foundation is achieved, typically about 2 to 4 feet deep, depending on terrain and expected train loads. Once the base is stable, engineers begin spreading the ballast. Unlike concrete, this layer isn't bonded together. It remains loose to absorb vibration and allow rainwater to drain freely through the track bed. 1 mile of track requires nearly 3,500 tons of ballast, around 7 million pounds of stone. The ballast is released from specialized hopper cars and then leveled evenly by a ballast regulator, a machine fitted with plow blades, rotating brushes, and laser-guided leveling boxes. Modern versions, produced by manufacturers such as Placer and Thor, can operate with minimal human input, automatically adjusting height and slope within minutes. After distribution, powerful vibratory compactors press the ballast into place, creating a dense and perfectly stable foundation. Completing just 0.6 miles of track can take anywhere from several hours to a few days, depending on soil conditions and site terrain. After the ballast layer has been evenly distributed and roughly leveled, construction crews move on to positioning the sleepers, the foundation pieces that define and lock in the exact alignment of the entire railway track. In most modern railway projects, this process is performed by an automatic sleeper laying machine. Using powerful hydraulic clamps, the machine lifts each sleeper, weighing between 600 and 700 pounds, and places it precisely according to its marked position. Each sleeper is spaced about 2 feet apart, and during a single shift, the machine can install more than 2,000 sleepers with remarkable accuracy. Sleepers can be manufactured from several materials. Traditional ones are made of wood, pressure-treated with creosote oil to prevent rot and reduce vibration. However, their lifespan is limited to around 20 to 30 years. Today, reinforced concrete sleepers have become the industry standard. Heavier, stronger, and capable of lasting over 50 years while supporting much greater loads. For maintenance or track renewal projects, engineers often use panel track systems, pre-assembled rail and sleeper sections built in factories. Once thousands of sleepers have been positioned with precision along the prepared route, the next stage begins: rail laying. Each steel rail, typically 78 to 80 feet long and weighing around 1,300 pounds, is delivered to the site on specialized transport vehicles known as rail trains. In modern railway construction, engineers often rely on continuous welded rails, CWR, long steel segments pre-welded at the factory, each stretching up to 1/4 of a mile in length. At the worksite, the rail train gradually feeds these immense steel ribbons from the rear, while hydraulic winches pull them forward and align them along the track bed. Workers guide the rails to glide smoothly over the ballast, positioning them perfectly atop each sleeper and holding them in place with temporary steel clips or pins. Once alignment is confirmed, the rail tensioning phase begins. Each rail is stretched or anchored using hydraulic tensioning machines to account for thermal expansion and contraction, a vital step that prevents future warping or buckling. After the rails have been perfectly aligned in place, the next step is to install the rail fastening system, a network of smaller components that keeps the entire track secure and stable. Each fastening assembly is made up of a steel base plate, rubber pad, spring clips, and anchor bolts. The base plate evenly distributes the wheel load from passing trains across the sleeper, while the rubber pad beneath it cushions vibration and helps reduce noise. Workers move steadily along the track, fitting each set of fasteners into position and tightening the bolts with torque wrenches to the precise specification, ensuring every joint applies the same uniform pressure. Once the bolts are secure, the clips are locked into place, holding the rail firmly against the base plate while still allowing slight flexibility for thermal expansion and contraction as the steel responds to temperature changes. Once the entire fastening system has been installed, engineers move on to the stage of track alignment and ballast tamping, a precision process that determines how smoothly a train will glide over the rails. A specialized tamping machine travels slowly along the track at an average speed of 0.3 to 0.5 miles per hour, equipped with dozens of hydraulic vibrating tines. During operation, the machine lifts the entire rail and sleeper assembly by about 1 to 2 inches, while the vibrating tines compact the ballast beneath at a rate of roughly 35 to 40 vibrations per second. This synchronized motion locks the crushed stones tightly together, creating a dense yet flexible foundation capable of absorbing impact and maintaining long-term track stability. Meanwhile, laser sensors and gyroscopes continuously measure elevation, tilt, turn, and alignment. Any deviation, even as small as 1/10 of an inch, is instantly detected, and the system automatically corrects it to match design standards. With this level of automation, a 1-mile section of track can be fully aligned and tamped in just 2 to 3 hours, making the process more than 10 times faster than traditional manual methods. Once the entire track has been precisely aligned, engineers proceed to the rail welding phase. 2 main techniques are typically employed: flash butt welding and aluminothermic welding. In flash butt welding, the 2 rail ends are clamped tightly together by an electric welding machine. A powerful current passes through the joint, heating the steel to nearly 2,700 degrees Fahrenheit until it softens, melts, and fuses into a single continuous rail. In more confined or remote areas where access is limited, engineers rely on aluminothermic welding instead. In this process, a mixture of aluminum powder and iron oxide is ignited inside a cast iron mold, triggering an exothermic reaction that can reach temperatures of up to 4,500 degrees Fahrenheit, hot enough to liquefy steel and fill the gap between the rail ends. Once the molten metal cools and solidifies, the excess material is trimmed off and the joint is polished using a rail grinder, removing any ridges or surface irregularities to ensure a perfectly smooth and seamless running surface. Once the entire rail line has been welded and ground smooth, the final inspection begins. Engineers use an ultrasonic flaw detector to scan the rails, detecting microscopic cracks or internal voids hidden deep within the steel. Flaws invisible to the naked eye. A track geometry car then measures elevation, tilt, curvature, and gauge width with precision down to 0.02 inch. Any deviation beyond tolerance is corrected immediately using tamping and alignment machines. When all readings meet standard, a test train is deployed to assess ride smoothness and vibration. It accelerates from 30 to 80 miles per hour, while hundreds of sensors record load and oscillation data. If the results fall within design limits, the railway is certified for operation, ready to carry its first train with precision and stability. build a railway capable of carrying thousands of tons of load every day, the most critical component is the steel rail, and its journey begins deep inside massive steel-making plants. Here, electric arc furnaces and blast furnaces operate at temperatures exceeding 2,900 degrees Fahrenheit, powerful enough to transform iron ore, coke, and additives into a uniform molten steel. An automated feeding system precisely measures each batch down to the pound, while temperature sensors and spectrometers continuously monitor the chemical composition. Heat-resistant robots stir the molten metal to remove impurities, while elements like manganese and chromium are added at exact moments to enhance strength and wear resistance. Once the desired composition and temperature are achieved, the molten steel is poured into molds, forming the foundation of the ultra-durable rails that will support the railways of the modern age. After being cast into billets, the molten steel is transferred directly into the soaking pit, where its internal structure is stabilized. Inside these heating chambers, temperatures are maintained between 2,200 and 2,300 degrees Fahrenheit by an automatically controlled combustion system. Infrared sensors monitor every surface point to ensure the billets don't cool too quickly. A sudden drop in temperature could cause surface cracking or deformation during rolling. Once stabilized, the billets move to the rolling preparation line, where massive heat-resistant rollers begin stretching and flattening the material. High-power hydraulic motors and gearboxes regulate the pressure, while the electronic control center gathers data from dozens of sensors to fine-tune speed and force in real time. This stage ensures the billets achieve a uniform size and sufficient ductility before entering the shaping process. The glowing red steel billets are fed into a continuous rolling line, where they are gradually sculpted into the signature eye-shaped cross-section of a rail. The process begins with the roughing mill, where large-diameter alloy steel rollers apply immense pressure to reduce thickness and elongate the material. In the intermediate stands, staggered rollers both press and rotate the billet, evenly distributing stress to prevent cracking. The final stage is the finishing stand, equipped with precision-grooved rollers that shape the eye profile down to the millimeter, with a thick head for load-bearing, a slender web, and a broad base to distribute pressure. Between stages, high-pressure water jets remove oxide scales and control temperature. Laser sensors continuously measure width, straightness, and contour, sending real-time feedback to the control center, which adjusts the roller gap during operation. A standout feature of modern rolling mills is their quick-change roller system, allowing different rail profiles to be produced without halting the line, an essential advantage in today's high-efficiency steel plants. As the rails exit the rolling section, they remain glowing hot and filled with internal stress. They immediately pass through a high-pressure water spray system, where a dense mist envelops the entire surface. Both the flow rate and spray speed are computer-controlled to ensure uniform cooling and prevent warping or distortion. Next, the rails enter the heat treatment zone, which includes quenching, tempering, or annealing furnaces, operating at temperatures between 900 and 1,100 degrees Fahrenheit, depending on the required mechanical properties. The combination of rapid cooling followed by precise heat treatment increases hardness, improves fatigue resistance, and preserves the sharp I-beam profile. Thanks to this process, each rail can endure millions of loading cycles without deformation, a critical requirement for the reliability and longevity of high-speed railway lines. After heat treatment, the individual steel rails are transferred to the welding line, where they are joined together to form continuous welded rail, seamless tracks stretching hundreds of feet in length. A system of guide rollers and laser sensors aligns the rail ends with sub-100th inch precision, within 0.01 inch. The flash butt welding technology uses a powerful electric current to heat both rail ends to over 2,700 degrees Fahrenheit, fusing them into a single solid piece under immense pressure. Immediately afterward, an automatic grinding machine removes excess metal, creating an absolutely smooth joint. The entire operation is monitored through a central control panel, which records key parameters such as temperature, pressure, and timing, ensuring every weld achieves the same strength and integrity as solid steel itself. The finished rails are then transferred to the automated inspection area, where high-speed cameras and optical sensors scan the entire surface at microscopic resolution. Meanwhile, ultrasonic and X-ray systems examine the internal metal structure, automatically rejecting any rail that fails to meet specifications. Random samples are tested using tensile machines, compression rigs, and Rockwell hardness testers to evaluate load-bearing capacity and deformation resistance. Each rail that passes inspection is laser-marked with a traceable identification code, ensuring full production transparency and consistent quality before shipment. So, you've just explored the entire process of how a railway track is built. Thank you for watching, and stay tuned for more fascinating stories from Mandarin Tech.